Okay, so welcome to our first case study, which is, to be honest, I love this sort of stuff. We're going to do a little bit of R coding. So we've got some, let's pretend it's coffee. And let's think about what we're going to do. So we looked in the last lectures about sort of general inference, etc. for linear regression. So what I've got here, this is RStudio. Obviously, here's my console over here, my file structure. Notice I'm using a project. Got a nice one ready to go. And here I'm using an R Markdown. So here's my YAML. We've got the verbal example. Week 2 is Jono. Some setup so we can compile this to HTML afterwards. And let's start by getting ourselves some libraries. So as you know, with R you have extra add-ons. The ones I'm going to use, we're going to use a bit of Tidyverse and GGLM, which you'll see in a while what that's about. So the best way of doing this is I've got a package here called the Pacman, which is package management. Remember the colon, if you've not seen it before, basically says the function pload, use the one that's in the package man one. And this is going to, what it does is if you have that package already installed, it just loads it so you can use the functions. If you don't, it installs them from the internet and then it loads them. So really nice. So let's give it a quick run. Run that. Right, so what we're going to do is we're going to try and predict wear and tear of rubber tires measured in grams per hour using the hardness of the rubber, which is a thing called Shaw units, and the tensile strength. Now the nice thing is this data is built in. It's called rubber and it's in the mass package, which is built into R. So we run that. And what I'm going to do is I'm going to quickly convert that to a Tibble. So a Tibble is a nice data frame. Just got some nice properties by using the Tibble function, and then we'll have a look at it. So you can see you've got 3 columns, loss, hard, and tens. So loss is how much loss you get. This is the hardness, and this is the tensile strength. What we should do next is, as you can see, the nice thing about Tibbles, it tells us exactly what we've got here. These are all integers at this point, int. So I'm also going to use the skimmer package. So we're just going to quickly skim R. And what this will do is just give us a quick exploratory data. So before we start doing any modeling, you should always look at your data, what we call EDA or exploratory data analysis. So let's see, it's telling us it's called rubber. It's got 30 observations altogether. That's the number of rows. It's got 3 columns. All the columns are numbers. And then for numbers, it gives us some information. So we've got no missing data. There's the zeros. The complete rate. The mean of loss is 175. The mean for hardness is 70.3. Tension 180. Then we've got our standard deviation. Then this is your minimum, your maximum, your Q1, your Q3, and your medium. So these are your descriptors. And it gives you a nice little histogram. If you try and compile this as a PDF, it won't work. All you need to do is do a quick skim without charts. See, it got rid of the histogram. So if you do decide that you're going to write your stuff in R Markdown, really good idea. You want to convert it to PDF so you can upload it. Just remember to use this command and you get rid of this hist. The hist it uses Unicode and your PDF can't work in LaTeX. So let's first of all, the first thing we should always do is look at our response variable. Our response variable is loss. So this is basically saying take your rubber, then, so I'll migrate, we're going to make a plot where our main variable is loss and we're going to do a histogram. So let's run that and have a look. It's a bit all over the place. There's not a lot to see there. Sometimes what I'll do here, let me just quickly highlight this, repeat it, and we'll do a geom density instead. Let's run that. Yeah, it's sort of maybe normally distributed. It's not particularly good. There may be slightly bimodal there. Yeah, all good. Now, the next thing we're going to do is I want to look at a scatter plot between loss and each of these predictors. And I want to do it all in one go. So the first thing I'm going to do is I'm going to use pivot longest. Let me just highlight this and see what this does. So what it does is it takes our thing and instead of having 3 columns, it says, right, I have an observation that has a loss of 372. And for the hard variable has a level of 45. For the tenths level, it has a level of 162. So it's taken this for the observations, which was loss, hard, tenths, and it's made it in what we call a long form. I can now pass this in and say on the x-axis put value, which is either going to be the hard or the tenths. On the y-axis put loss. Give us some points. Then geomwrap, say give me a separate scatter plot for each of either hard or tenths. And also we'll put a little smoother on, and I'm going to do a linear model smoother. So when I run that, here's what we get. So we can see that in both cases we have a negative slope, a negative relationship between loss and what we're predicting in case this is hard and tens. These are quite widely spread. It's not a stronger relationship. These are quite nicely, quite tight around that. Okay, so that gives an idea that there's some sort of relationship there, maybe a nice linear relationship. So let's fit a model. So LM, short for linear model. Everything to the left of our tilde, that's that little squiggle there, is our response variable, in this case loss. Everything to the right is a predictor, so we've got tens, we've got hard, and we tell it where the data is. And I'm going to save that in an object called rubber_lm. So next thing I'm going to do, we're going to use the standard. Let's have a look at our summary. So what we got here, we have, here's the formula we did, here's some residual information, but the main thing we got, here's the estimate of beta 0, here's beta 1, here's beta 2, here's the standard error, so that's that SE square root of CJJ. If you wanted to see that X transpose, the variance covariance, I think you can go COV. Is it COV? No, it's VCOV. So this is your diagonal, will give you your variance of your estimators, and this is the covariance between them. And so if you took the square root of the diagonals, that should give you these numbers here in the standard error column. Here's your t-value for testing if this is equal to 0, and here's the associated p-value. So pretty strong relationships in all of these. You know, the standard cutoff is 0.05, and these are all less than 0.05. We also have things like residual standard error, the multiple r squared, the adjusted r squared, we'll talk about them later, and the F statistic. This F statistics I'll show you in a second is basically going, let's compare this model with the model that just has an intercept. And we've got these values. You may have in the past thought to yourself, wouldn't it be really nice to get this out as a data frame so I could have it as a table, I could filter, I could select? Well, you can using the Broom package. So in the Broom package there's a thing called tidy. And all that does is it returns this as a data frame, which is really nice. If you want this other information, you know, multiple r squared, etc., you use the glance function. So here you can see it's got the r squared, the adjusted, the test statistic, everything. Really nice. Very useful. The Broom function is really good of getting information out of models. So we have a significant relationship between loss and tens, a significant relationship between loss and hard, as shown by the p-value. But you might want to say, well, is this model any good? Is it better than just having an intercept? Now, I said that that's what this is testing here. Ta-da! So let's actually test that. So what I'm going to do is I'm going to fit a new model called the null model. And the null model, basically, my response variable is loss, and all I've got is an intercept. And now what I'm going to do is I'm now going to do an ANOVA between the null model and my model with the two predictors. Oops. Like that. And here we've got our ANOVA table. So here's your residual sum of squares for both models, your degrees of freedom. But let's go and see how it compares with our summary. So let's go back and redo our summary. And let's see, you should, first of all, the 1.76 times 10 to the minus 11 is the p-value we got for this model. The F statistic is 70.997, or 71 if you round it, 71 if you round it. You've got 2 and 27 degrees of freedom, 2 and 27. So to some extent, this bit, just the last line of your normal summary statistic, is an ANOVA between the model and the model that's just the intercept. And that ANOVA, we'll come back when we do model checking, you can do this idea of sort of, you're basically splitting your sum of squares and say, how much is explained by one model, how much is explained by another model, how do these compare once we adjust them. Our basic model, as always, is y equals x beta plus epsilon. We assume that epsilon is, normally distributed with the mean of 0 and a constant variance, or what we call homoscedasticity. We should check that. Now, the old way of doing it was with the plot function. There's a new thing, a new package called ggplm. Really nice. I'll show you what it does. It produces all your classic plots. So here's your residual versus fitted. Check the assumptions. If our linearity assumption is correct, which is that y equals x beta plus epsilon, it's that model, there's not an extra relationship we have to describe. We should get random scatter. That's got random scatter. We should also check for homoscedasticity. There's a couple of ways, but the classic one we do is the square root of the standardized residuals against the fitted. And you can see that this is, the blue line is giving us an idea of how the variance changes. Not particularly bad. This is our normal QQ plot of the residuals. We want this to be roughly linear. It is. This is all about leverage, and we'll talk about that a lot later. I think that's week 3 or week 4. Okay. You could do this the old-fashioned way with the plot. And if you've done this before, you hit each one and it gives you individual plots. So there's the residual versus fitted. There's the normal QQ plot of the residuals. Those is the scale location plot, as we call it, which is the square root of the standardized residuals. I'm going to talk about residuals a bit more in later lectures, versus fitted. And that's it. This is your residual versus leverage plot. And again, we will talk about this. We can also do prediction. So what I'm going to do is I'm going to say, well, what would be my point prediction if I had a hardness of 70 and a tens of 180? So I'm going to make myself a new little data frame, just like that. So just a single row that I want to predict for is 70, 180. If I just use predict with my model and just give it that data, it just gives me a point prediction that the loss would be 177.8269. If I wanted to predict the 95% confidence interval of the average loss of all tyres that had a hardness of 70 and a tens of 180, I would use my confidence, like that. And this is the lower and the upper of the 95. If I wanted to ask about a single individual tyre, what do I predict its loss to be? I would use prediction. And hopefully you can see that this is wider than this. I wanted to get that concept across the wideness. So what I'm going to do here is we're going to make ourselves a nice little plot. So let's break it down. I create myself a tibble. And the tens will all be equal to the mean. So I'm setting the mean to the tens. But the hard, I'm going to have 100 points going from the minimum hardness in the data set to the maximum. So let's run that and have a look at it. So the tens is all 180, but here it starts with 45, 45.4, 45.9, etc. I'm then going to predict both the prediction interval, which I call predint, and the pred confidence. So if I run this line, and we just have a quick look. This has got my point prediction for each of those rows, the lower and the upper. This one does the same with the confidence. And I'm now going to add those. I'm going to take my new points. I'm going to add some new columns. I'm going to have a column called pred, which basically I go to pred interval and grab the column called fit. I then get pred lower, which is the prediction intervals, the lower column, the upper column, etc. So let me show you what that does. It grabs all the points. There you are. You've got tens, hard, pred lower, pred upper, confidence lower, confidence upper. And what I want to do is I want to do a plot where I have this on the x-axis. I'm going to have a line for this, a line for this, a line for this, a line for this, and a line for this. So let's get lead. First of all, we're going to pivot longer, but we're going to keep tens and hard out of it. So let's have a look at what that's doing. Basically, what you've done is said, right, for tension of 180 and hardness of 440, for 45, I've got a point predictor of 341, I've got a lower bound of 260, etc. So now I'm going to pass that into ggplot, hard on the x-axis, the value on the y-axis, the colour is going to be the name of this. We're going to add some lines, and we're going to add the points from the original data underneath. And this is going to look like this. So here's the points from our data. Very nice. This is our point prediction line. This is the relationship between, in our case, our loss and our hard when we've set our tens to the average. If you think about reality, it's actually, in this case, a big flat plane in three-dimensional space. But we sort of went, let's just look at the case where we just lock tens in. This is our upper and lower confidence interval. A couple of things to notice. As you get further away to the edges, notice how it gets wider. This is our upper and lower prediction interval. Notice that some of the points, on average 5% of our points, will lie outside of in this case, the purple and the blue line. You'll notice again, it gets slightly wider at the edges, not quite as obvious as the confidence interval, but it's definitely wider than the confidence interval at all points. Nice little plot to illustrate that prediction confidence. So there we are. There's our first case study. I'm going to come back to these regularly because I think seeing this, the R Markdown and the HTML that I get that. So what do I mean by HTML? I can give this a quick knit to HTML. It will run it. It seems to be doing well. And hopefully it will spit out for me a lovely little report. All my plots, all my code, all my analysis sorted. If you don't know R Markdown, go learn it. Really, really useful. Okay, there's your first case study. Next week, I can't remember what I'm doing next week. It doesn't matter. I will find out by then. Anyway, hope you enjoy that. See you next time.